This talk introduces a new optical gating method of imaging biological deep tissues, which we call space gating. Improving the imaging depth of optical microscopy has been a long-standing goal in the field of bioimaging. While imaging with light provides good enough resolution for observing from tissues to cells, intracellular structures, and even biomolecules, imaging capabilities experience severe difficulties when imaging thick, highly diffusive biological structures. One of the main reasons is optical property called multiple scattering, which obscures the so-called ballistic wave that carries object information. When light propagates through transparent medium and hits a target, the sensor elements can collect the information carried by ballistic waves. In an ideal imaging condition, the images can be reconstructed by the ballistic waves from every point of the target object. However, when light passes through highly scattering medium, such as biological tissue, we cannot know which signal is from the desired target, thereby making it very difficult to reconstruct an image. In general, the intensity of multiple scattering components is inversely proportional to the depth of sample, but the intensity of ballistic component exponentially decreases as the scattering mean free path of a sample increases. The scattering mean free path, LS, is an optical property. Usually, biological tissues have a few hundreds of micrometer of LS. There have been several attempts at extending the imaging depth by applying various gating operations and using ultrasound modulated light. As explained earlier, we need to gain more ballistic signals and less multiply scattered signals. In particular, selecting the signal of interest and blocking undesired components is called gating. Several gating techniques have been developed, such as confocal, time, and polarization. Especially, time gating reduces multiple scattering signals by using the difference of arrival time, as the ballistic components will undoubtedly have the shortest path length. Another technique is called ultrasound modulated optical tomography, which uses an ultrasound focus with high frequency that modulates the optical frequency of light. Since sound wave can penetrate biological tissues without much distortion, it acts as an effective guide star for detecting light via the important phenomenon called acousto-optic interaction. Despite its penetrating depth, such technique does not have a high resolution compared to other optical imaging methods because the resolving power is set by acoustic focus size. Whenever a sound wave propagates through a medium, it varies the material's permittivity due to mechanical strain. It is in fact a special case of photoelasticity, which is a change in the optical properties under mechanical deformation. In such variation, the material now acts as a grating for propagating light. This means such light experiences diffraction with frequency modulation. Our new technique called space gating is based on this effect, making use of ultrasound focus at the target plane as a spatially gating window. While ballistic components passing through acoustic focus are surely modulated, a large fraction of multiple scattering components that are spread in space can miss the gating window. This leads to the dramatic decrease of multiple scattering noise. For our detection to work at its best, we use holographic phase microscopy with an acousto-optic modulator, an ultrasound transducer, and observe through specifically fabricated sample tray. In order to prove the performance of our technique, we provide a useful factor called noise suppression ratio, which is an estimation of improvement over the noise due to multiple scattering. Such factor increases up to 100 times better as the total optical thickness increases, where we used a light-absorbing target embedded between front and rear scattering media. Without space gating, the results show that the images suffer from severe degradation, whereas the images contain visible objects with space gating. To prove the effectiveness of space gating, we demonstrate non-invasive and label-free imaging results of biological samples. The first notable result is the phase image of red blood cells within scattering media. The cells are clearly visible on the right where space gating is applied. The other result is the intensity image of zebrafish muscle fibers. Especially, we acquired the large field of view image with high resolution of optical imaging. The scale bars in the images E to J indicate 10 microns. In order to image inside a highly diffusive media, such as biological samples, we have to overcome the noise due to multiply scattered light. There are several techniques for reducing multiple scattering components, such as time gating, coherence gating, and ultrasound modulated tomography. We demonstrate a new technique called space gating that uses acousto-optic interaction. This technique successfully suppresses the noise, thereby making it possible to image within biological tissue. Further development of space gating will provide an important step towards reaching the ultimate imaging depth set by the detection limit of ballistic waves.